Hi everybody. My name is Sam Pandit, and I'm currently a sophomore at J.R. Tucker High School. And today I'm presenting here from Richmond, Virginia. So as someone who has been like relatively interested in computer science since joining high school, I've been able to like research online, just explore the field due to like parent influence and also the fact that computer science is like one of the most important skills today, right, in the current century. So with some, brief research, I was able to stumble upon machine learning, obviously one of the hottest topics right now. And as a result, I kind of chose that to explore in my Polygence project. So specifically, thanks to the help of my mentor, Clayton, I was able to narrow down my topic of study to ARIMA, a specific algorithm called, which stands for Autoregressive Integrated Moving Average. So ARIMA is basically an algorithm that's used to forecast and predict data, specifically called time series data. And time series data is basically data that follows a regular time interval. So for instance, monthly time series data would look like January, February, March, April, etc., right? Constantly and consistently. So a common form of time series data that well fits the criteria is obviously stock prices. They're constantly and consistently changing over time. And you can look at them from various standpoints, right? So you can look at them from a yearly standpoint, monthly, daily, or even hourly, right? So they're a great example for time series data, and that's sort of the perspective I chose to look at as I conducted this project. So for some background, the four variables of ARIMA are P, D, Q, and S. P stands for the autoregressive component, which basically accounts for how far back the algorithm is going to look to make today's prediction, right? So from a stock perspective, if P was set to 1, that would mean like the ARIMA model would look back to yesterday's price to help predict today's price. So the next value is D, which stands for the integrated component. And this basically talks about how many times the data is going to be made stationary. So stationary data is basically data that has constant means and variance, making an ARIMA algorithm having an easier time to actually analyze it. So the higher if D was set to 0, right, that would mean that the data is already stationary and we can like automatically start analyzing it without error. But if D was set to a higher value, we'd have to undergo a process called differencing, which basically is subtracting the previous data value from the current one to get that the data at a constant to give it more stationarity. So lastly, we have Q, which stands for the moving average component. And this basically covers like how many past forecast errors the algorithm looks at to help make its prediction. So if Q is at a higher value, once again, at a stock context, that would mean that there's a lot more like past like spikes, dips, and fluctuations in the data. So therefore the algorithm is going to rely on it a lot more to help make its prediction. So lastly, we have S, which is sort of like an outside variable in this case, and it stands for seasonality, and is used in a different algorithm called SERIMA, which is relatively similar. So like I talked about, time series data, how you can analyze data from any time interval. Seasonality is able to account for that. So you could look at a data set from, any time interval. So for instance, if you looked at a yearly seasonality, you would set S to 12 to account for each month in that year. So with this research, I was able to help create a tool thanks to the help of my mentor on Google Colab, which basically says whenever you enter a stock value, it's able to shuffle through the code, and generate the best ARIMA model and then create a graph. So the data that we got with the closing prices was from Yahoo Finance. That was our source of data. And as it creates that data, it's going to go through a graph of training, testing, and predicted data here, as you can see on the side. And you'll notice that a majority of the data is training data. And this really emphasizes how much data the ARIMA model is going to need to, make its prediction, right? And then you have the other two values of the actual price and the predicted price. So it relies a lot heavily more on the training data to then actually make its final predictions. So you might notice that the predicted price doesn't look like as accurate based on the graph, right? But the point is you don't want it to look at like following like that specific like up down up like curve there, as you can see the dark blue. As long as it's following that general direction, here is slanting upwards, it's most likely going to be accurate. And from here you can't really tell like what the real accuracy is. So down here in our last chunk of code, my code has provided like measures of accuracy, and specifically the most important one is MAPE, which stands for mean average percent error. And to calculate the accuracy here, I've provided a brief formula. So I set a variable a here, which means MAPE multiplied by 100. So as you can see there, our MAPE is 0.0139. If you round it to a decimal, it'd be about 1.4%. So then to find the accuracy, you would do 100 subtracted from this value, and that would give you about 98.6%. So this really does show that in this case, Amazon, the graph is and the predictions were pretty accurate. So with this tool, I was able to generate a website and I was able to make it so that it explains ARIMA in a relatively simple fashion to users. Here, I'm breaking down the components of ARIMA and the variables, and I'm also providing a brief, intro about it in the top section there. So the goal was with this was to basically give users an easier time to understand these kind of complex algorithms, because that was something I sort of struggled with when I first stumbled upon machine learning. So I felt that I was very much able to achieve this goal, as my mentor did provide great feedback regarding it as well. So in terms of next steps, I would say that I want to try to implement ARIMA into predicting like future prices, right? Not just like current ones. That would definitely be a really cool idea. So with that, I do conclude my presentation, and I thank you all for your time.
Awesome. Well, aside from the obvious question of what you're going to do when you retire at 18 from predicting the stock market and knowing when everything is going to go up, I am curious, Sam, if you could go back to the model, the chart.
Yeah. Okay, let me see. I'm not sure why it's not. Okay. Yep.
Zoom just isn't liking presentations today.
Yeah.
So I'm curious. So we talked about the kind of 4 hyperparameters for the ARIMA model, right? The P, D, Q, and S. So forgive me for not remembering perfectly, but is D kind of like how far backward it's looking?
Yeah, that's gonna be P. So D is basically how many times. Yeah. D is like how much the data is made stationary. So that's using a process called differencing, which is like subtracting a current value from the previous one. And that works to make to give it that stationarity effect. So
cool. So could you clarify for us what your p-value is here then? For this prediction, did you specify a specific p-value? What is it and why?
Yes. So for this specific prediction, let me shuffle back here. So basically, yeah, with our code, it's kind of like in Google Colab, there's it's sort of just like shuffles through. Let me find it. Sorry. My apologies.
No rush. And for the audience members as well, feel free to drop a question in the Q&A if you have a question for any of the speakers as well. I appreciate you pulling up the notebook live. That's awesome.
Yeah. So
let's chat about it.
Here, it looks like P is going to be 0. That's like sort of our star P value. So it's kind of using like the training data, not necessarily looking back at a specific value, but it's going to use like that training data to help it make this current prediction.
Totally. So if you were to guess, then we're looking at a predicted price line. If you were to guess, let's say we change P and we increase it, so it's looking backwards a considerable amount. How do you think that that would impact the predicted line? Would it go like further up? Would it go more straight, or would it go maybe further down? Do you have any thoughts?
Yeah, so I think the further back P would look, the line would probably go a little bit more upwards, making the prediction just a little bit more accurate because it does have more context. But I definitely think for the value, obviously, it's going to go a little bit more down, and the prediction might be a little bit less, as accurate. So.
Totally. Yeah, I think the cool thing here too to remember is that that like how far back you're looking also impacts the reliability of the prediction. So it's an important decision. Cool. We got one more question from the audience as well. So you picked the ARIMA model. Is there any other methods you considered? Is there any other methods you know of that could have tackled the same problem from a different vantage point?
I think the one thing that I talked about before was the SARIMA, which used like seasonality to account for as well. So that's something different besides ARIMA. In terms of other forecasting models that I've heard of, I believe there's things like long-term, short-term memory, that I haven't really touched upon too much, to be honest with you. But I say the two ones that I'm most confident with are ARIMA and SARIMA for sure. But there are a few other predictor algorithms out there. Yeah.
Absolutely. Yeah. And if you are ever interested, I recommend looking into random walks. That's a super interesting kind of subgroup analysis that came out of the stock market that's being applied kind of across the data science field. Super interesting. Great. Thank you so much, Sam.
Yeah. Thank you.